yesterday we have introduced the basic notion of three-diagonal decomposition, and I just recall very briefly the definition. If you have n, an integer, a natural integer, you say that a three-diagonal decomposition of the polynomials of degree less or equal than n is determined by a triple, three objects. So it is determined by a sequence of subspaces which are pre-Hilbert spaces with respect to a scalar product. So K goes from 1 to n. Then you have a sequence of operators, which are the creation operator, and this is labeled by the index j. Remember that we are dealing of measures, probability measures on Rd. So we have d variables, and the capital D is the set of indices. And then we have jk, and we have the creator that goes from 1 to n minus 1, because it creates, and it will go from pk to pk plus 1. So the last index is n. And then we have the preservation operators that instead they go from 0 to n. So there are some properties of this triple, and let me recall that the fundamental property is this. Fundamental properties are that each pk is a monic subspace. Recall that monic subspace means that the monomial basis is perturbed, each monomial is perturbed by a polynomial of degree, each monomial of degree n is perturbed by a polynomial of degree less or equal than n minus 1. So in this sense, it's a small perturb, small with respect to degree. So each pk is a monic subspace of the polynomials of degree less or equal n. We already say that A is the restriction of the creator to the space pk, and A0 are self-adjoint operator for this scalar product. Once we have, but the fundamental property is that the restriction of the coordinates on the space p n minus 1 are symmetric. They are symmetric operators for which scalar product? For the unique scalar product that we denote by the symbol on the, this is a scalar product on this space. And by definition of monic subspace, remember, monic subspace means that they satisfy, in particular, the induction relation. So, by repeating, since each pk is a monic subspace, I have a direct sum decomposition of the polynomials of degree less or equal than n as a direct sum of all the pk for k from 0 to n. The fundamental property is that when I have these scalar products on each of these space, I can define a unique scalar product by taking the direct sum of the single scalar product, the orthogonal sum of the single scalar products. So orthogonal sum means that with respect to this decomposition of polynomials of degree less or equal than m as a direct decomposition, this becomes, in fact, as a direct vector space decomposition, this becomes, in fact, an orthogonal decomposition in the sense of pre-Hilbert spaces. Okay? So, let us sum up. The three-diagonal decomposition has some important properties. And yesterday, now what we want to do? We want to, yesterday we have shown that given a state phi, which is a state on the polynomial algebra, which is a star algebra, I associate to it a three-diagonal decomposition of P. So now I want to introduce, we introduced yesterday the notion of three-diagonal decomposition of P. I recall again very briefly. We have defined three-diagonal decomposition of the polynomials of degree less or equal n. Now imagine that for each n, I give you such a three-diagonal condition with the compatibility condition that all the objects that the restriction of the three-diagonal decomposition on Pn on all pk with the k, let us say ph, use another letter, ph with h less or equal than n, they are obtained by restriction of the scalar product, the decomposition. So the spaces don't depend on n. This is what I want to emphasize. When the space, a priori, in this definition, all these objects may depend on n also. I have written only the dependence on k, because I anticipate my future notation. I am interested in those decompositions in which these spaces don't depend on n. They are only depending on k. And so I will have, when n goes to infinity, I will have a full decomposition of the old polynomial algebra. In terms of monic subspaces, which now are orthogonal. Orthogonal for what? For the scalar products induced by phi. And all these phi k are the restriction of this scalar product induced by phi on the monic subspaces of the decomposition. And now we want to prove the converse. Now we want to construct, however, the problem is how to formulate this, because in this formulation we started from the scalar product and from phi. But to prove the converse, we have to construct this scalar product. And we will construct it step by induction. First of all, let me recall you something that we already mentioned last time, namely the fact that we deduce non-commutativity from commutativity. Recall that we have the decomposition of the self-adjoint operator xj, which are the coordinate operators. This is the so-called quantum decomposition, canonically associated to the measure mu on Rd, which is the joint probability distribution of this d random variable. You can consider that d real valued random variable are a single vector valued random variable. This is standard in probability theory, okay? D-dimensional vector valued random variable. Now, the fundamental property is that when I consider these random variables as multiplication operator acting on this algebra, P by left, the polynomial algebra, by left multiplication, left or right here is the same because the algebra is commutative, of course, then these are commutative operators. So the commutator is 0. And if you write the quantum decomposition of xj, which is these three terms, the quantum decomposition of sk, which is these three terms, you obtain a total of 9 terms. But they are grouped in this way: 4, 2, and 3. What is the grouping? The grouping is by degree. When you have a gradation of any vector space, the homogeneous operators are those that preserve each space of the gradation. And then you have the operators of degree 1, which shift the space pk to pk plus 1. Degree 2, pk plus 2, and so on. So we have this commutator, and we have these commutators, and we can easily compute what are their degree. For example, this operator has 2 plus, so it has degree plus 2. It brings, I create twice. It doesn't matter which order, because any creator brings from k to k plus 1. And so iterated application of another creator will get to k plus 2. So this commutator will have a range in the space pk plus 2. But this operator creates only 1, because A0 is a preservator. So it increases of 1 the degree. So this operator will bring me in k plus 1. This operator, similarly, will bring me in k minus 1, because I have so this will be preservator, and this will bring in a minus 1. And this is preservator again. This is minus 1, and this is minus 2. You see? So what happens is that, however, the pk in our gradation now has become orthogonal gradation. So the ranges are orthogonal. So if a sum of operators with orthogonal range is identically 0, it means that all the homogeneous components are identically 0, separately. And these are the commutation relation, because I separate the homogeneous terms, and I find creator is 0. This implies that annihilator is 0 because I take the adjoint. Then there is this commutation. Pay attention. This commutation is very special of probabilistic origin. In usual quantum mechanics, well, we will have to discuss what is A0. But for symmetric measure, remember that A0 is identically 0. There is symmetric measures are characterized by the property that the preservator is identically 0. So this is absent in symmetric measure. And you have this commutation relation here, you see, that connects creator and annihilator of different indices. See, this is some interesting commutation relation. It's not the usual commutation relation that gives in the usual quantum illusion, when you have a product measure, you will see, I will not discuss it, I have no time, but this is a theorem we proved with Kuo and Stan. The product measure are characterized by the fact that this commutator is delta JK. And this is the standard commutation in quantum mechanics. But this is a more subtle commutation. Because you see, here I have J with plus, but here I have J with minus. So this is a relation that has not been met in quantum mechanics, because quantum mechanics only considers product measures, for which this relation will be identically 0 equals 0, and a trivial identity, okay? But in general, we can consider non-product measures. So these are why I recalled this. I recall these relations because I want to emphasize the fact that they are deduced only from the commutativity of the xj. So in our framework, the xj are given, so they commute. So if we have any construction in which the xj commute, and we have the quantum decomposition, this commutation relation will take place. We don't have to worry. We don't have to impose them as a separate necessary condition. This is very important, because these are quadratic relations. If we had to impose them as a separate necessary condition, we would be in great trouble, because we would have to solve quadratic equation in operators, which is a very difficult task. Okay. So now let me recall again this definition of, let me fix the notations. I call LA for 2 Hilbert space. Well, this is not a star algebra, because it's a star algebra only when H is equal to K. Of course, otherwise I cannot compose 2 operators if they have different ranges. But if A is equal to K, we have a star algebra, and the point is that not all operators are adjointable. There are some conditions, even in finite dimensional spaces, because at pre-Hilbert space level, we need that an operator to be well defined. It must map the 0 vector of one space, 0 norm vector in one space, to the 0 norm vector of the other space. This is the compatibility condition for the existence of the adjoint. And I will often use, remember EJ is the canonical basis of CD. And we use very strongly the fact that this is a basis of the real is a real basis, in the sense that CD is a direct sum of RD plus I RD, and the canonical basis is real. Okay, so here is the notion that I have recalled on the blackboard, but is good to keep it in mind, so I wrote on the blackboard, of 3 diagonal decomposition. So I have a sequence of subspaces for Pn. Each of it is monic. Remember, monic means real basis, first of all. Second, that there exists a linear base of each pH, which is a very special structure. The highest degree is a single monomial. possibly with a non-zero multiple of a single monomial. And there is an additional term which of degree strictly less than the degree of the monomial. So, and this is monic degree of the monic basis of degree h means that the highest monomial has degree h. And this automatically implies that the sum is direct. It's a simple algebraic calculation. So first I have this. Then I have on each, I have a prescalar product on this space with the two important properties. First, that this decomposition is orthogonal, and therefore every restriction is orthogonal. Second, the coordinate operator are symmetric. You see, why the restriction is on p and minus 1? Obviously, because multiplication by coordinate increase the degree. And I have the scalar product only up to n in my definition. So I must restrict it to a lower order in order to give a meaning to this scalar product. And the last is very important. The last is very important. You see, in some sense, what we are trying to do, we are trying to do, when I have this diagonal, this infinite decomposition, I obtain it as a limit from this decomposition when n grows to infinity. If I obtain this as a limit, at each step up to n, I will form the new decomposition, which will be with the new index n plus 1. What is the minimal information I need to go from n to n plus 1? How many parameters, how many objects, new objects I need to go from this to n plus 1? I don't know if somebody of you knows the theory of stationary processes. The whole decomposition of a stationary process does exactly this similar idea for a stationary process. It's decompose it into a martingale, and the martingale part is the additional, what is called in probability theory, the innovation part. So sometime I will use the same word, innovation, to mean the additional information that I have to go from n to n plus 1. So in this theorem, in this definition, we see that we will have the third part of the definition is very important, that we need to have the creator and the preservator for each k. So for each k, but pay attention, when I use this notation, I am emphasizing that these are pre-Hilbert space operator. So when I put the scalar product and not only the vector space, I emphasize that zero norm vectors are mapped into zero norm vectors. Okay? This is an important property. Then the same for this. But here the spaces are different. Of course, the creator is different. Remember, the creator is for k from up to n minus 1, and annihilator up to n. So what are the two properties of the creator and annihilator? First, the preservator must be self-adjoint for the k scalar product. See? And this identity must take place. This is the restriction of the quantum decomposition on the pk space, what in quantum mechanical language is the k particle subspace. And this must be true for each n up to n minus 1. Why n minus 1? You see, because the annihilator is the adjoint of the creator. And the creator at the nth level will go to n plus 1. To speak of the adjoint, I need a scalar product of n plus 1. But in my definition, there is not yet. This is the additional information we want to put. Okay? So I have to restrict my condition on the up to n plus 1. And you see, I use always the same adjoint operator. But of course, this is an adjoint that depends on indices. It depends on k and k minus 1. So it depends on k. So it will be understood tacitly that this depends on k. When confusion may arise, I will emphasize this possibility. Okay? So that is why I emphasize it here. Star, I don't put index k on star, but it depends on k. A posteriori, we know that it will not depend. So what is the point? First of all, the decomposition that we have, whatever the orthogonal decomposition is always independently of the state, since it is a monic decomposition, is a direct sum in the sense of Hilbert space. This is the sum with the dot, means direct sum in the sense of, in the category of linear spaces. And then this is what I said before with this identity. To give a n separate scalar product on each factor of this decomposition is equivalent to give a single orthogonal, a single scalar product, which is the orthogonal sum of the single particle or single degree, let us say, polynomial. And we will use very much. So I will indifferently speak of a single product on the polynomials of degree less or equal than n, or n different scalar products on the single factor pk. And this is also what I said before. In general, these objects, pk, and also the scalar product a priori, can depend on n. We will not use this in our definition except in the following definition, because this is important. It's the fundamental point that I anticipated before. We introduce the notion of extension of a three-diagonal decomposition. So we start from a three-diagonal decomposition of p, the polynomials of degree less or equal than n. And we want to say when such an object that is a three-diagonal decomposition of the polynomials of degree n plus 1 is an extension of this. As I mentioned before, the obvious definition is that in the extension, the only new thing is the space when k is equal n plus 1. Because all the spaces up to n are already in the previous definition, okay? So the obvious definition is that the space coincides whenever k goes from 0 to n. Similarly, the scalar products restricted to of n plus 1, restricted to the previous, to the polynomial of degree less than n, must be compatible with the previous scalar product. And third, the preservation operators and the creators must be compatible whenever the index is not the maximum one. So they belong to also to the preceding three-diagonal decomposition. So from this you see that essentially what I need to go from this three-diagonal to this three-diagonal, which is the innovation, the new information I need. From this definition you see that the new information is only at the n plus n+1 level. So it is one operator H which is self-adjoint. In fact, D operators, because one for each element of the basis. This is the dot here, okay? And then I need the creators only at k equal n, the last one. But then I need the scalar product. And there must, so I need three new things, okay? In fact, we will see in a moment that only two are necessary. So the extensions will be parameterized by two objects. And so finally, I will say that a three-diagonal decomposition of the full algebra is a sequence of spaces which are now independent on n. So that I write simply independent of n, because the spaces are all the same. Okay? The scalar product is defined, and depends only on k, not on n. The creator only on k, and the preservator only on k. Notice that if I have an extension, this is very important, the assignment of the creation operator is the new element that I need. But this assignment plus the scalar product uniquely will define the A minus. Because we know that, you see, the operator A minus J, J, remember, is the component, is EJ, and the index J goes from 1 to D, while the index K goes from 1 to n or n+1. So the creator will be a map from n+1 to n. We want that the scalar product on n+1 is such that the adjoint of the creator is the restriction of the annihilator on the n+1 space. So once I have the creator, you see, the creator brings from n to n+1, I uniquely obtain the annihilator and this will exist because by assumption the creator preserves the zero norm vector, so it has an adjoint. And of course, any three-diagonal decomposition induced by restriction at the three-diagonal decomposition of the lower order subspaces. And now we have the fundamental theorem. You see, if you remember, in the case of the one variable, there is a one-to-one correspondence between a self-adjoint operator, which have all moments with respect to the identity, to the matrix element in the identity operator, and pairs of Jacobi sequences. Principal Jacobi sequences, which is positive and satisfies a compatibility condition. I will write the two Jacobi sequences, omega n and alpha n. This is the principal Jacobi sequences, which is not only positive, but has the famous compatibility condition that omega n equal to 0 implies omega n plus k equal to 0 for all k greater or equal than 0. This is the one-dimensional seed, the root of the preservation of the zero norm vectors. In the one-dimensional case, this is exactly the condition that the operator preserves the the creation operator preserves in this case, annihilation, the zero norm vector. Now, we have this proof, which is the basic point that justifies the importance of the notion of three-diagonal decomposition. So we have introduced the three-diagonal decomposition. And now we claim that every state on phi on P uniquely defines a three-diagonal decomposition. We, in some sense, have already implicitly proved this part of the theorem because we have constructed the three-diagonal decomposition. But the converse is important. Conversely, every three-diagonal decomposition of this polynomial algebra uniquely defines a state with the fundamental property that I have a three-diagonal decomposition, conversely, and I define a state. Having defined the state, I can now apply the construction of the first part of the theorem and produce the three-diagonal decomposition of this state. The theorem is that the two coincide. Okay? In this sense, we have established a one-to-one correspondence. To give a state is the same as giving a three-diagonal decomposition. And so, well, the first part of the proof we already did, because we know that if the scalar product is given by a state phi, then necessarily the multiplication operator by coordinates are symmetric. And necessarily they have a quantum decomposition. If I restrict the quantum decomposition on the single factor n of the gradation, of the orthogonal polynomial gradation, I obtain a three-diagonal decomposition. This is simple. The converse is more subtle. Suppose that I have given now a three-diagonal decomposition of P. So remember, this means that I have given a direct sum decomposition of P, which is orthogonal for this scalar product defined for n equal to infinity. And I have given a sequence of creation operators, which are constructed in a certain way that will be crucial. Now you will see in what sense. And a sequence of preservation operator, which is less important, and we will see that it can be arbitrary. This reflects the one fact that we know in one dimension that the secondary Jacobi sequence is made up by arbitrary real numbers. Okay, so we will have the perfect analog in multi-dimension. Now, remember that in the definition, in the requirements of the three-diagonal decomposition, there is this requirement that the restriction of xj on Pn minus 1 for each j are symmetric. But now I have it for every n. And when n go to infinity, this absorbs all polynomials in a finite sense. Okay? So if they are symmetric on each p n minus 1, they are symmetric. So we have the symmetry with respect to the full scalar product. But if you remember the lemma that we proved yesterday, that there is a one-to-one correspondence between symmetric scalar products for which the xj are symmetric and states on the algebra P of polynomials. So since we have proved that they are symmetric, we have a state. Okay? What we have still to prove? We have still to prove, so we know that the prescalar product is induced by a state by the lemma that we proved yesterday. Once that we have the state, now we want to prove that the canonical decomposition of this state with respect to the phi state coincide with the given one, with the three-diagonal decomposition from which we started. Okay? So how do we do this? Well, this is relatively simple now, because from the definition, we know, remember, this is an extremely important point when I said we have three objects for three-diagonal decomposition: the scalar product, the creator, and the preservator. However, the creator is defined inductively by the previous one because the xj are canonical, they are algebraic, they are independent on any probability measure. So once I have the xj and the quantum, I know that if the quantum decomposition exists, it must verify this condition. So I have no freedom on the creator. The creator is given once I give the preservator. Okay? And if you look, the creator will go to n, from m to n plus 1. The preservator remains in n, and this, which is the annihilator, but it is corresponds to the creator of n minus 1, which I have because I have the nth or three-diagonal decomposition. So I can put up the induction. And moreover, I have this by assumption. This is the definition of a minus n. So, you see, simply now I take the minus and I bring it on the other side, and this identity I rewrite in this way. And then I sum over all n, and this is the restriction on Pm, but the gradation gives me the full polynomial algebra, so I recover the x. And so I have this decomposition. This decomposition is a gradation. This decomposition is made of the three parts, which are increasing preservation and decreasing part. And we have proved in the yesterday lecture that the quantum decomposition of the xj is unique. So these operators, which are those of the three-diagonal, they must coincide with the creation and annihilation operator defined by phi that we have found during the proof, because of the uniqueness of the quantum decomposition. And this proves the theorem. Okay? Now, we have established this one-to-one correspondence, and now we want, what we want to do? We want to give a less abstract, we want to give a constructive. How? Since there is a, I want to reproduce the analog of this theorem. Okay? So this is a very constructive theorem because it tells me take any sequence of positive numbers only restricted by this condition. Take any sequence arbitrary of real numbers, then I give you a state on the polynomial algebra. Okay? And I want the analog for the multidimensional. What is the minimal, what is the analog of these two Jacobi sequences? Well, the first step, I do the step from m to n plus 1. So given a three-diagonal decomposition up to n, can I classify all possible extensions? And then you see, if I can do it in one step, then by iteration I will be able to do the full classification. because the construction will be done step by step. Okay? So if I am able to solve the problem for one step, I will be able to solve the problem for each successive step. So we anticipate for this. The classification will depend on an important notion, on the notion of a positive definite kernel on a C-star algebra. I gave the general definition here. This is well known, I think, even if I cannot give you a precise reference, but it surely will. We used very much in the stochastic limit this kind of construction, but is a operator generalization of the positive definite kernels, which are well known. And in fact, they are well known when you study Hilbert modules, because you can, in some sense, prove that Hilbert modules are in one-to-one correspondence with positive definite kernels. So the important point is this. You see that this is if omega is a scalar, this is the standard definition of positive definite kernel. And here I replaced the condition that it is a scalar from the condition that it is an operator in a star algebra. In the concrete case, our star algebra will be the star algebra of linear operators of a pre-Hilbert space into itself. Okay? So, for such a star algebra, the notion of positivity will be given by the scalar product. So, why I need this definition? So, it's clear what it is. In our case, the space V will be the space C to the power D. The complex d-dimensional space. And in a previous lecture, I explained from where the positive, I will show again in the proof, but the intuitive reason why positive kernel appear is obvious whenever you have creator and annihilators. Because what is the creation operator? We have defined A daga J n is applied to a vector Cn, okay? And this goes into the polynomial of degree n plus 1. So I can multiply this by AK, let us say AH daga, always on n, and another vector eta n. And the scalar product will be the scalar product in n plus 1. But by construction, this operator must have an adjoint, which is the annihilator at the level. So this is a Cn A daga Jn adjoint A Hn of eta n. But now the scalar product is n. So this will be our positive definite kernel. Remembering that J means the basis, the canonical basis, this will be, this is, let us call it n plus 1, because this will define, is called n plus 1 because it's the kernel of the n plus 1 scalar product. So you see, so we have a EH, and this will be applied to eta n and multiplied scalar by Cn. So you see, this is a scalar product. The EJ are a canonical basis in CD, and so this gives on CD a Hilbert module, a two-sided Hilbert module, on which algebra? On the algebra of, well, this is the algebra of adjointable, the kernel omega n, you see. This goes up, this goes down, this remains. So I am omega n plus 1 e j e h is in the linear adjointable operators of P n. I don't put scalar product, there's no space. Pn is a pre-Hilbert space. Okay? So this is fundamental observation, but very, very simple. That is how these kernels arise. You see? And so from this point of view, you can consider this kernel. See, there is a famous theorem by Kolmogorov that every positive definite kernel you extend rather easily to operator kernels. Every kernel is a decomposition. So we see that the creator of, sorry, this is creator. The creation operators are in some sense the Kolmogorov decomposition of the positive definite kernel, which defines the scalar product in the n plus 1 particle space given the scalar product in the n particle space. Huh? So this is the idea why kernels arise. And this is the condition of positive definite. As you see, G is a subset of the space K. And U, V, and this should be U. This is a mistake, a misprint. U, UV, not VV. Okay. So now I need a lemma. This lemma I put in very abstract form because to emphasize that this is a purely algebraic lemma, it has only to do with monic basis and the scalar product. I don't need the symmetry. I can take an arbitrary scalar product, not necessarily for which the coordinates are symmetric. So, if I have two monic vector subspaces, and I have a pre-scalar product on the polynomials of degree less or equal than n, then I give two arbitrary maps. The only condition I require is that A0 maps Pn into Pm. I don't care self-adjoint. Then A minus maps Pn into Pn minus 1. The algebraic result is that. Then this is the crucial point. Remember, when this is a preservator and this is a annihilator, this is a necessary condition on the creator. The creator must have this form if it exists. Then I define the linear span of the creator. So you see the innovation, how the new space arises from the old, how the n plus 1 arises from the old. Then I say that necessarily this is monic. It's a monic subspace. I use very, very strongly the structure of the degree filtration of the polynomial algebra. Why is monic? It is monic for the following reason. By definition, Pn is a monic subspace. So there is a real linear basis which is a perturbation of monomial basis. Now you remember what is perturbation of monomial basis. I said many times. I don't repeat. You remember. It's true. Okay. Yeah. the higher level is only one highest level, and then you perturb by a lower order polynomial, a single monomial. So this Xi and H is an element of the monomial basis. By definition, the creator will bring this operator into this operator, into this, this vector into these vectors. However, by assumption, this is a polynomial of degree how much? This is of degree n, and this is preservator, therefore n. And this is degree n, but this is lowers of 1, the degree. So this is degree n minus 1. So this sum is a polynomial less of degree less or equal than n. Okay? So, on the other side, Xi and H is a monic basis, is an element of the monic basis. So, it is a polynomial of degree n. And the highest degree is a single monomial. The single monomial gets multiplied by xj. But j is arbitrary. I can vary in all possible ways. Of course, when I multiply a single monomial of degree n in all possible ways, and then I vary this single monomial among all monomials of degree n, I get all possible monomials of degree n plus 1, by definition, of degree of a monomial. Therefore, by varying Xi and H in the monic base in all possible ways, and xj among the coordinates in all possible ways, I will obtain all possible monomials of degree n plus 1 now. So this is of degree n plus 1. And this is, moreover, of course, multiplication by xj doesn't change the real linear character. We have to stop. Maybe another one should begin. Okay. 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 The 2 minutes I give you the statement that the all extension, if I give a tridiagonal decomposition of degree n, all extensions are parametrized by these pairs. A positive definite kernel, which is the analog of the omega n, and an arbitrary self-adjoint operator, which is the analog of alpha n. And the proof will be postponed when I come back from Bangalore. Okay? But we achieved our goal, to parameterize all extensions of a given tridiagonal decomposition. Thank you.